or you can stay with me depending on your viewpoint on it. I'm super excited. College theme presentations are my favorite, so we're going to be talking about water today. If you didn't know the song that was on when you came in, I'm sorry for you. Vanilla Ice, Ice, Ice Baby, right? It's a water presentation. I take no credit for this, by the way. I spent the 5 minutes before my presentation brainstorming with other faculty in Macomb yesterday on what song I could use. Bob Zellman suggested Ice, Ice Baby. So this is a shout out to Bob, that was his song, not mine. So we're going to be talking about water. I know you're all sitting there, going, why are we talking about water for 20 minutes? I already know everything I need to know about water. I promise you don't, okay? Guys, water is weird. It's really, really weird. It does things that we don't actually fully understand. It does things that we don't expect. It doesn't follow the rules of, patterns and things that we do for other compounds on the periodic table and elements on the periodic table. It's just weird. Okay? We're still learning a ton about water. As a matter of fact, true story, I had this presentation done last week, and then on my Google News feed over the weekend, as I'm scrolling through my Google News feed, there is an article that they have discovered a new form of ice. I didn't even know amorphous ice existed. So I'm not going to get super technical, but we are going to get into some of the little details of chemistry today. Amorphous is a solid that doesn't have a regular structure. Generally speaking, that means the shape can change. So like rubber is a really good example of an amorphous solid. Okay, it's a solid by all definitions, but it's a little stretchy, right? Probably the chairs you're sitting in, not really an example of an amorphous solid. Okay, there are now officially 3 forms of amorphous ice. Not 1, but 3. This is a rabbit hole I could go on probably for years because I don't understand it, but it's true, it happened, and it was just published in Science over the weekend. Okay, and if you don't know science, science is like the high journal of science. It's why it's its name. It has like an 8% acceptance rate of articles that are published in Science. So to be published in Science is a big deal, okay? But I promise you don't know everything there is to know about water. We don't know everything there is to know about water, okay? All right, so if we're going to talk about it, we need to talk about what it is. I know you all know what water is, but we're going to talk about it in terms of things you might not have learned before. 2 hydrogen atoms, 1 oxygen atom. Super simple, okay? Doesn't get a whole lot simpler than water. It has a mass of about 18 AMU. So what does that mean? AMU is an atomic mass unit. It's something we have essentially made up to talk about something super small. You can't see a water molecule. I can't walk into the lab and put a water molecule on a balance and get a mass. That's not how this works. So we have created a unit so that we can talk about these things in terms of scale, okay? To give you something to compare to, you are breathing in oxygen and nitrogen as we speak, okay? O2 and N2 that have a mass of, nitrogen is 28 AMUs and oxygen is 32. Yeah, basic math, 32. Okay, so water technically has less mass than both oxygen and nitrogen, which you are breathing in and don't see. Really small, and yet it is literally everywhere. This is what it looks like. Don't freak out, it's gonna be fine. Although if you've been in or are in a chemistry class, this should not freak you out. So you've got an oxygen in the middle, 2 hydrogens that are attached to it. These dots up here are electrons. So the oxygen has some electrons on it that the hydrogens don't. This leads to an interesting property. Water is polar. It is by no means unique. There are hundreds of millions of polar compounds in the universe, but it's super important that water is polar, okay? If water wasn't polar, we wouldn't exist as we know it. Most of the things that you interact with, many things are polar, and generally as a rule, polar things like other polar things. So water likes a whole lot of things you need. Okay? If it was non-polar, it really wouldn't like all of the things that you need. So not unique, but super important. Because I can't not. A little more science. So when I say something is polar, it's like a magnet. You know how you have a magnet and it has like 2 sides, right? That's basically what polar means. It has 2 sides of a molecule. The oxygen, having more electrons, is technically more negative because electrons are negative. The hydrogens are more positive. It's not the same as saying it's a full negative, full positive. It's like, I always equate it to static electricity. It's like there, but not real electricity. Like you couldn't power anything on static electricity. Okay, it's kind of like that. It's this uneven distribution that causes water to be polar, which is really, really important. Okay, it is based on something called a tetrahedral. I'm going to put it on the screen, and I want you to tell me the shape you're looking at. What is that shape? What does that look like to you? I know what most of you think this looks like, because it looks like it to me. What would you call that if I put it up on the screen and didn't tell you what it was? A pyramid. It looks like a pyramid, okay? Sometimes the naming in science makes a whole lot of sense, and sometimes it doesn't. That looks like a pyramid, but we don't call it a pyramid. There's a different configuration that we call a pyramid. We can't call two things the same, so this in science is a tetrahedral. Tetra is 4, so it's a 4-sided figure, right? So if you think of your pyramid, you've got the 3 sides plus the base is a 4-sided figure. In this example, the little orange dot would be your oxygen. It's set up in the middle. So it's not flat. The oxygen kind of exists in the middle, and then the corners would be your hydrogen and your electrons. It is technically called bent. Water is bent because of this oxygen-hydrogen. Okay, it's literally bent. But it's based on that tetrahedral. So there's a little nuance there. If you want more of the details, come take a chemistry class. I will skip on none of the details, I promise. And for those of you who have taken a chemistry class, you probably know I skip on none of the details. All right, so why are we talking about this? Because this leads to some really interesting properties, okay? Ice floats. Did you know that? I'm sure you knew that, because you see it all the time, okay? Do you know how weird it is that ice floats? It's super strange. It's not actually supposed to happen like that, okay? Not unique to water, but it is really weird, all right? When something goes from a liquid to a solid, your particles become more organized. Liquids are disorganized, solids are more organized. How many of you have a pile of laundry sitting at home waiting to be folded? That just is like a mountain. No? Okay, a couple of you? Yeah. If you fold that laundry, it takes up less space than if it's sitting in a pile in your basket or on your bed or on your chair or wherever it is that you pile your clean laundry, waiting for the 2 weeks to fold it.
Why?
Guilty. Sorry, Becca. Guilty as charged.
That was cheating.
Sorry, Jamie. You're standing right next to each other. I apologize. Yeah, so it gets more organized, right? And it gets smaller. That's what usually happens. When something gets smaller, but has the same mass, because fundamental law of the universe is you can't change mass, okay? So it has the same mass, it gets smaller. Something called density goes up. When the density goes up, you usually technically sink, okay? Water does exactly the opposite. When water freezes, it gets bigger, which you knew if you've ever had the misfortune of putting a can of pop in the freezer and you left it there and you didn't catch it before it exploded. It will explode. I don't recommend you try it. That's not a go home and try it thing. It is a mess to clean up. It's not fun. But water expands when it freezes because of the shape. That tetrahedral shape makes it expand, causes it to be bigger. So water gets bigger, mass is the same, density goes down, and it floats. Weird. It's just weird. It's important, but it's weird. Okay, the next and this is the one that's like really important and super extra weird, is the boiling point, all right? In science, in chemistry, we look for trends, and we use the periodic table to help us define trends. If we want to know how something is going to behave, we look at the things that are around it. So if we want to know how oxygen is going to behave, we're going to look at the things that are in the same column. Typically, columns are similar behavior, okay? So if we want to know where water is supposedly going to boil, we would look at the others in its column, okay? So if you look at the others in its column, this guy up here is the one at the bottom, then you got the one in the middle, SE, and then S is down here. You might not be able to see it because you might be a little bit distant. These are all negative numbers. The highest boiling point here is, I think, negative I don't know, 2, 3, somewhere in that range, Celsius. Okay? So if you follow the trend, if this is the bottom of the row and this is the top of the row, then oxygen should be somewhere down there. Which means, in theory, water should boil at like -70 degrees Celsius, which is -94 degrees Fahrenheit. No, I did not do that in my head. Yes, I did that calculation before I came in here. I'm not that good. But it's like -94 degrees Fahrenheit is where it would boil. So what does that mean? We should not have liquid water. All of the water on our planet should, in theory, be a gas. That would be real bad. We would not be happy campers if all of the water on the planet was a gas. Okay? We know water doesn't actually boil at -70 degrees Celsius. What's the boiling point of water? And I don't care if you give it to me in Celsius or Fahrenheit. Anyone know? Some of you should know. 212 Fahrenheit. Very good. 100 degrees Celsius. Okay? Oops, we're too far. That's where water actually boils. Way, way higher than it should. And importantly so, because otherwise we'd be dead. Okay? But why? Why is this a thing? I've gone too fast again. It's fine. All right, so why does this happen? This happens because of something called hydrogen bonding. Okay? Hydrogen bonding is really important to the boiling point of water, but also to some other things. So what is this? Some polar molecules, and they have to be polar, are super special. Okay? And they're super special if they have oxygen, nitrogen, or fluorine with a hydrogen attached to it. Spoiler alert, water's got 2 hydrogens attached to it. Okay? When that happens, remember that distribution of electrons, that polar, what we were talking about, becomes really, really big. And the size of that distribution matters. Okay? Some things are a little polar because it's just a little bit different. Some things are really polar because they're really different. These guys, these oxygen, nitrogen, fluorine bonds, are really different. So they're really, really polar. And because of that, they can do this thing called hydrogen bonding. So it's not bonding in the traditional sense that you would think bonding in chemistry. A lot of the times I describe it as if something is bonded together, it's kind of sort of super glued together. It's not going to move unless you really put some effort into it. This is not that. This is more magnets interacting type bonding. Sometimes really strong, but still able to be pulled apart. Okay? So this is what a diagram of hydrogen bonding looks like. All of these dotted lines would represent a hydrogen bond. So then you see the oxygen, the hydrogen, and then your dotted lines are a hydrogen bond. So what this does, when you boil something, right, you are attempting to boil a liquid, you are attempting to move the molecules from the liquid stage to the gas stage, right? You have to give them enough heat to basically be ripped out of the liquid stage and thrown into the gas phase. That's what you're doing, okay? The more of these dotted lines you have, the more hydrogen bonds you can make, the harder that is. The more sticky it is. It sticks together more. So it takes more energy to throw it off into the gas phase. Water can form up to 4 hydrogen bonds, which is what makes that difference between what should be -70 and is actually 100, okay? The others, nitrogen, fluorine, my other hydrogen bonding pairs, they cannot make 4. Water is the only molecule that I know of, I'm not saying it's the only one in the universe, it's the only one I know of that can form up to 4 hydrogen bonds. Okay? There's not a ton of things that will hydrogen bond. No, the pool is really limited. 3 elements plus hydrogen out of 118 can hydrogen bond. So your pool is extremely limited here. Okay? So water is the only one I know of that can form 4. The nitrogen and the fluorine usually form 1, maybe 2. So they also boil higher than expected, but that's not what this talk is about. Okay. Another super important aspect of hydrogen bonding, it's not about water, but it is really important about hydrogen bonding. Your DNA, the way your DNA pairs, the base pairs in DNA are determined by hydrogen bonding. Okay, if you know anything about DNA, you know your base pairs have 2 very specific, they have a partner and they don't mix, right? There are 2 pairs that you can have and there is no mixing between them. And it's because one of those pairs can form 2 hydrogen bonds and the other pair can form 3. So they're not going to mix because they like to form the maximum number of bonds that they can form, and that all goes back to this. Same deal though, oxygen with a hydrogen, nitrogen with a hydrogen, fluorine with a hydrogen. And I will be honest, I do not know which one is in the, I think it's nitrogen with a hydrogen for DNA, but I'm not sure. The other component that you need is a pair of electrons on that oxygen, nitrogen, or fluorine. That almost always happens, so it's not something that we spend a whole bunch of time focusing on. But it's really cool. It's really, really cool and really weird. That's all I got. But I stretched that out because I didn't say a lot of that yesterday, so I like it. It worked out well for me. I would welcome questions, comments, any sort of what blew your mind about this. Did I bore you for 15 minutes? Because that's fine if you tell me that, I won't be offended. Did you know all of this? What was new or exciting to you? I'm seeing lots of shaking heads in the back. What you got? Questions, comments, anything?
For one of the pictures, I think it was like the very last picture.
Yep.
One of the oxygens I think there was 2 oxygens that was touching hydrogen or something like that.
Let's look. This picture?
One oxygen was touching 2 separate hydrogens.
Yep. Yeah, this guy right here.
Yeah.
So each of these, remember in the picture I showed of what it looked like, it had those two pairs of dots, right? So each line is a pair of dots.
Okay.
So one of the pairs can attach itself basically to this hydrogen, and the other pair can attach itself to that hydrogen.
But they don't always.
They don't have to. This would be like the maximum number here with 4. Okay. So you've got your hydrogen, and then your 2 pairs. They don't have to do that. You could get it with just 1 pair. It just depends on what state you're in and how much energy the system has. But 4 would be the max. It could be less than that. Good observation.
It looks like a clan marriage.
Yeah.
I'm just saying.
It's fine. It's fair. Yes, Raj.
So what happens when you boil this? What happens to structure?
So what's happening when you're boiling it is you are giving enough energy to basically break these dotted lines, and then this individual water molecule, when it has no more, it's going to vibrate itself into the gas phase. So the structure of water as a gas is just individual water molecules. They're just moving.
Oxygen or hydrogen?
Not oxygen or hydrogen, it stays as a water molecule, just as a gas. If you want to take this water and break it down into oxygen and hydrogen, you got to supply some sort of current or electricity to do it. Although, interestingly, I believe that is one of the ways that they are looking at using hydrogen as a fuel source, is to take water, if you put enough of a charge through it, you actually get oxygen and hydrogen out, and then hydrogen burns. It's one of the ways that they use hydrogen fuel cells to power cars. That's what they're looking at. I think they're using it in California as we speak, or they're trying to. Yes?
Professor Loftus, if water was all gas, could we theoretically live if we somehow ingested the gas like water?
Sure,
Okay.
absolutely. And we could take the gaseous water and condense it into a liquid. It's just energy intensive to do that. And to do that would require someone to be here to do that. And getting essentially down to that negative 70-degree mark is pretty darn difficult. So yes, in theory, we could survive or we could adapt, evolve to do it. But yes, Amy?
But
No?
we wouldn't have any food.
Aha, there you go. See?
There are some organisms that have to have liquid water. Like plants don't have a pumping system. They have to have liquid water to do it. We have a pump that moves our fluid around. They don't, and they take advantage of the liquid characteristics of water and its cohesiveness and adhesiveness. They wouldn't exist. They couldn't function.
She knows better than I do about that, so biology instructor knows better about it. Other questions? Yes?
So are you saying that water is like the most resistant to become a gas more than the other elements? Is that why the boiling is?
Yes. So I don't know if it's the most resistant on the periodic table, but it is more resistant to become a gas than it should be. Yeah, which is why it requires more energy to do that, which is why if you ever boil a pot of water, you feel like it takes forever, because it just sits there. It has to absorb all of this energy in order to get into the gas phase. Anything else? Closing thoughts? I have 12:40, so we're right on time. All right, thank you.